In this segment, we introduce a means to represent all pixels in an image as a vector. This then introduces an alternative way for representing the degradation equation in the restoration problem. It becomes a vector matrix equation. If the degradation is LSI, then this degradation matrix has a specific form. It is a Bloch-Circulant matrix. It is straightforward to describe this matrix in the spectral domain by finding its eigenvalues and eigenvectors. We study this property, which allows us to take the degradation equation to the frequency domain, something, of course, we know we can do based on the material we covered in week 3. The reason, of course, we devoted this lecture to study this alternative representation of images and the matrix vector version of the degradation equation is not to just do some math, but because they provide a flexible representation of images and systems that process them. And they're also useful since we can now easily borrow tools and results from linear algebra and optimization theory in providing solutions to these inverse problems we are interested in. Before we proceed, we'd like to introduce a vector notation for images and then a matrix vector notation for the convolution equation. So let's assume we have an image of dimensions n by m. So this is the image here. The standard way we've been using so far to represent an image is x, n1, and 2, where n1 ranges from 0 to n minus 1 and n2 from 0 to m minus 1. We would like to represent this two-dimensional array, this image, as a one-dimensional vector. So I'd like to write this image as a vector x. And now vectors can be shown in boldface or sometimes with an underbar or an overbar. It should be clear from the context that a vector is involved. So one way to do it is to take each row of the original image. So here's row 0, row 1, row n minus 1, and turn each row into a column vector. So this is row 0 transpose, so it comes here, row 1 transpose, all the way down to row n minus 1 transpose. So the n by m image is now converted into an n m times 1 vector. So this is the process of stacking an image into a vector. And if the stacking is as shown here, I stack by rows, then it's also referred to as lexicographic ordering. So it should be clear from now on that this functional representation, x function of n1 and 2, and this vector representation can mean the same thing in what follows. Let us consider the one-dimensional convolution of two one-dimensional signals, x of n convolved with h of n. Let's call the result equal to y of n, and we know that this is equal to the sum over k, x of k, h, n minus k. Let's assume for simplicity that x of n has support from 0 to n minus 1, n samples in other words. H of n has support from 0 to L minus 1. And as we know, the result of their convolution will have support the sum of the limits of the support, so from 0 to n plus L minus 2. I would like to consider all the values of the signal y and stack them into a vector. So I'd like to form the vector y0, y1, all the way to yn plus L minus 2. So this vector is an n plus l minus 1 by 1 vector. So this will be equal to a matrix here that will multiply the signal x. So here's x0, x1, x of n minus 1. So x clearly has dimensions n by 1, and therefore this matrix has dimensions n plus l minus 1 times n. So if we follow the steps of the convolution, we take h, we flip it around, find h of minus k, and then shift it by n. We can see that y0 is equal to h0 times x0, y1 is equal to h1 times x0 plus h0 times x1. Then I'll have here this row of h's, and the rest of the values here not shown, they're all 0. So if I call this a vector y and call this matrix H and then a vector x, I wrote in matrix vector form the result of the convolution. By considering all the values of the signals, I can kind of combine them all into this matrix vector form again, y equals hx. We observe that H has this specific form, that is, the values along each diagonal are equal, and this is referred to as a Toeplitz matrix. We'll see next that by modifying the signal and the matrix, we can write indeed the matrix vector form for the circular convolution, and then this matrix H is going to have another form which we'll call circular matrix. I would like to perform the circular convolution of x of n with h of n, so that the result of the circular convolution equals that of the linear convolution. In order for this to be the case, I should carry out the circular convolution with period n plus l minus 1. Let's call this y of n again. So this means I should pad x of n with l minus 1 zeros and then carry out the circular convolution. So if I do the same thing here now, which is to put all the values of y into a vector, this will be equal to a square matrix now, multiplying x. And x, I'll have the original values of x, 0, 1, all the way to n minus 1, and then I'll pad it with zeros, and the number of zeros is equal to l minus 1. So if we look at the structure of H here, this matrix, it will have H0 on its main diagonal, H1 on the diagonal below it, all the way to HL minus 1, will be 0 here, and then at this corner will be H1, H2, HL minus 1, and I'll have, let's say here, HL minus 1, and 0 everywhere else. It's easy to verify that indeed the values you obtain here by carrying out this matrix vector multiplication are equal, these y values, to the values we obtained from the linear convolution as shown in the previous slide. So again, I can write y equals hx. H now has also a special structure. The structure now is that if I take any row of H and I circularly shift it by 1 to the right, then, and circular means that the element that leaves the matrix due to this shift to the right wraps around, it appears at the other end of the row, at the beginning of the row. And I can do this for all rows, including the last row. So if I circularly shift the last row, I'll obtain the first row. So this matrix is called a circulant matrix and has some useful properties that we will talk about next. We saw in the previous slide that if I use a matrix vector representation of circular convolution, I end up with a circulant matrix. Here's a simple example of a 4x4 circulant matrix. So the elements of the first row are these, A1, A2, A3, A4. I generate the second row by circularly shifting the first one. So this is A1, A2, A3, A4 wraps around and comes at this place, A1, A2, A3, A4 wrap around, and finally A1, A4, A3, A2. So clearly for this 4x4 matrix, if I know the elements of its first row, I can define the whole matrix, since again, each row is generated by the circular shift of the row above it. So if I look at the general matrix H, it's a circular matrix. The elements of the first row are H0 to Hm-1. I don't write the remaining of the rows since, again, will be circular shifts of the first one. For any circular matrix, finding its eigenvalues and eigenvectors, which is by and large a difficult problem, is rather straightforward. And this is so because, let me first denote by lambda and w its eigenvectors are the w's and lambda are the eigenvalues. So the eigenvectors of any circular matrix are known in advance. The nth eigenvector is equal to this. And one should recognize right away that these are the basis vectors of the discrete Fourier transform, these complex exponentials. And the set of eigenvalues are simply the discrete Fourier transform values of the first row of the matrix. So again, a very straightforward and important property of circular matrices. So the singular value decomposition of the original matrix is simply equal to this. I put the eigenvectors here as column vectors of the matrix. The eigenvalues become the diagonals element of a diagonal matrix. This matrix is the first one, actually it should be 0 here, the first one, -1, it's an invertible matrix. So I can write any circular matrix H as WD W-1, where again D is this diagonal matrix that has at its diagonal the discrete Fourier transform of the first row of the matrix. Based on what we've seen, let's assume I have the circular convolution of x of n, circular, let's say length n, with h of n. Let's call this y of n. We know from the study of the discrete Fourier transform that I can take this equation to the discrete frequency domain, where the convolution becomes multiplication. So these are the discrete Fourier transforms of the corresponding quantities, and this is an endpoint DFT. So k goes from 0 to n minus 1. Now we saw that I can take this equation here and write it as a matrix vector form, where H is a block circular matrix, and we did see that H can be written also, its singular value decomposition is equal to this, and therefore from here, if I pre-multiply by W minus 1 both sides, this becomes equal to this. It can be easily shown that W minus 1, a signal, is the discrete Fourier transform of the signal. So this is the DFT of y, all the values, and this is the DFT of x. So this gives me, this is a vector clearly, so this vector gives me all the values of the DFT of y, and D is a diagonal that has as its elements the DFT of H, so this is H0 to H n minus 1, and here is the DFT of X. So we see whether we're working with a pointwise here version of the circular convolution or the matrix vector form of the circular convolution by either taking the DFT here in a straightforward way. I end up with a pointwise relationship in the discrete frequency domain as shown here, or by considering the spectral decomposition of the matrix H, which is circulant, I end up with the matrix vector representation of the discrete Fourier transform. So this is something very important to keep in mind that we will be making use multiple times. Based on what we have discussed so far, if I have a linear system H that accepts F as its input, and then noise is added at its output to form the observation Y, I can represent this system in the matrix vector form as shown here by stacking, and lexicographically, more specifically, stacking the images into vectors. Now, if the system, in addition to being linear, is also spatially invariant, then the input-output relationships of this system are represented by the familiar by now two-dimensional convolution. In this case, the matrix H has a special structure. It's now a block circulant matrix, which means that it is circular at the block level. So you see, if I take the first row of blocks and shift it circularly, I will obtain the second row of blocks, and I keep going. If I take the last row of blocks and circularly shift it, I will obtain the first row of blocks. But each block is also a circulant matrix. And that's the definition of the block circulant matrix. As a matter of fact, if, let's say, for simplicity, H here has a first quadrant support, and this is the 0th row, this is the first row of the impulse response, this is the m-1 row, then the 0th row will be used to form the submatrix H0, the first row, the submatrix H1, and all the way to the submatrix Hm-1. So this impulse response that I show here is all it's needed to form this block circulant matrix, because for each block I need its first row, and then that's all I need because it's circulant at the block level. The story with block circulant matrices is the same as with circulant matrices I mentioned earlier. So if H is a block circulant matrix, it can be decomposed as shown here. W has as elements the eigenvectors of H, which are the two-dimensional complex exponentials of the two-dimensional DFT, and D here is a diagonal matrix with elements the stacked values of the two-dimensional DFT of Hij. So then, if I start with the observation equation as shown here, I substitute the value of the decomposition of H here, and then I pre-multiply with W minus 1 to obtain this. So W minus 1 Y represents the stacked values of the two-dimensional DFT of Y, and similarly W minus 1 F represents the stacked into a vector values of the two-dimensional DFT of F. So in other words, this equation is equal to Y equals D F plus N, where again here I have stacked the two-dimensional DFT of the image Y. I have stacked into a vector here the two-dimensional DFT values of the image F, and D is a diagonal matrix that has the DFT values of H. If I look at one element of Y, since D is diagonal, is going to give me one element of the discrete Fourier transform of the image Y. So each entry of this vector Y represents in the point-wise here frequency UV. These are discrete frequencies of the DFT. In what follows, we're going to need some very basic elements of linear algebra that I would like to mention here. So given an n-dimensional column vector X, the L2 norm of the vector squared, it's simply X transpose X. It's a scalar, and this is equal to the sum of Xi squared. So applying this to a term like this, the definition of the norm, that is, this is Y minus Hx transpose Y minus Hx, and if I carry out all the cross multiplications, this is equal to this. Right? These are all scalars, these are inner products, and the one is the transpose of the other, therefore they're equal, and this becomes equal to Y transpose Y minus 2 X transpose H transpose Y plus X transpose H transpose Hx. We'll also need the notion of the gradient of a functional of a norm. This is by definition, this is a vector, an n-dimensional vector that has the partial with respect to x1 of the norm squared all the way to the partial with respect to xn of the norm squared. And if I use the expression for the norm I just showed in the beginning, it's the sum over I x of I squared then clearly if I look at any of these partial derivatives, there is only one term that depends on the particular x of I. So the first term, there's only one term depending on x1, so this is 2x1, down here it's 2xn, so this is equal to 2x. So applying this definition, you should be able to verify that the gradient with respect to x of x transpose y is equal to y, while the gradient with respect to x of the quadratic term here is equal to 2 times h transpose hx.